Good morning, everyone. Thank you for attending the first ever EAG Coffee and Conversations with EAG experts. My name is John Mosquito. I am one of the account managers with EAG Laboratories, and I will be starting us off with an introduction of EAG, and we'll then introduce the rest of the team to you as we move along. Today's agenda will include an introduction to Eurofin's EAG Laboratories. Then we'll segue into contamination measurements. Here we'll be looking at three types of, we'll have three presenters, three different sets of techniques and the thought processes and decision making and questions we will ask you to help determine the right analytical techniques for your particular question regarding contamination. The first will be surface analysis, and that'll be presented by Jia Lu, talking about our surface sensitive techniques like XPS and Auger and time-of-flight SIMS. Next will be organic contaminations, and that'll be presented by Jannica Schneider, talking about FTIR, nano-IR, Raman, GCMS, and LCMS. And then finally, we'll close with metallic and inorganic contaminations with Luc Picard, and he will be talking about XRF, TXRF, and other techniques such as that. Finally, we'll close with a question and answer period with EAG people, including our presenters, myself and Ian Moat, and then go into deeper conversations as you would like, so we can answer your specific questions. And then obviously optional would be a tour of the Sunnyvale labs here, and that'll follow after that. Introduction to EAG. EAG has been here in the semiconductor space and working with you for over 45 years with materials testing services. We are a service lab. We provide analytical services to over 5,000 clients in 20 different labs located primarily here in the United States, but also including labs in Europe and in Asia. We are IP secured and ITAR registered, and we are also additionally accredited and certified across multiple industries and markets. Really what we are your partner in analytical services to help you understand and analyze your materials, to help your internal labs, and to give you more capacity to get your job done. EAG is owned by Eurofins. It's a parent company based in Europe that is a multi-billion-dollar global leader in scientific services. Over 900 laboratories are part of the Eurofins network, and we are just one of those, but we specialize in failure analysis, in semiconductor materials, in medical device. So we are here, we have, within the Eurofins network, we have the expertise to help you understand your contamination issues. Again, Eurofins and EAG Laboratories specifically is across here in California, across the United States, and also the rest of the world. We help a diverse range of industries, from semiconductor, where EAG started, consumer electronics, aerospace and defense, automotive, medical device, energy, chemicals, pharmaceuticals, whatever industry you are in, we can use the techniques and our expertise that we have and the experience that we have to help you solve your problems. EAG Laboratories serves the entire life cycle, and so we're here to partner with you from R&D, product innovation and improvement, troubleshooting, quality assurance, manufacturing support, failure analysis, regulatory compliance, supply chain and quality control, and litigation services. Now here is our SMART chart, formerly called the bubble chart. SMART standing for spectroscopy, microscopy, analytical resolution tool. And we'll be referring back to this chart time and time again during these presentations to kind of orient you to all the different techniques possible and how we're going to compare and contrast each one of them. So what we have here on the x-axis is analytical spot size. Typically, that's how large of an area that the technique will sample at any one time. But really what that means is how small of an area that it can be analyzed. So when your contamination is centimeters in size, we have many techniques that can look at that area. But when you get down to millimeters or microns or even nanometers, we still have techniques that are viable and can be used in the analysis for contaminations. And then on the y-axis, what we have is concentrations. Each of these will give you elemental, molecular, or chemical information, and at different levels. Whereas at the top, we have percent levels from 100% down to 1%. We have many different techniques that are available to characterize that contamination. But then as we get into the parts per million, into the parts per billion, even into the parts per trillion, we still have analytical techniques that we can bring to bear to help you understand your materials and contamination issues. Outside of the box, we have our bulk techniques, which include techniques such as GCMS, LCMS, ICP, and then down here at the bottom, imaging techniques. And these include SEM, dual beam fib, focused ion beam, and TEM. These techniques will, again, not necessarily be quantifiable, but will give you an image and help you understand your systems and the contaminations that we're dealing with. In addition to spot size, we also have the Z direction, the depth of analysis. So again, for every opportunity or contamination that you may have, we have a technique that will be in the sweet spot of the thickness of that region to analyze. Whether you need to be in the very top surface using time of flight SIMS, OJ, or XPS when you're within the first few angstroms of the surface, to deeper techniques like SEM, IR, FTIR, Raman, and even deeper into the bulk techniques like XRD, XRF, and ellipsometry. Some of these are also showing arrows. Those are techniques that can give you a depth profile. So composition as a function of depth. So it can be very powerful in understanding not just where what the contamination is, but where does it lie within your layer stack. Now, I'll be introducing now Dr. Jia Liu. She's a senior scientist here at EAG in Sunnyvale, and she'll be talking about surface analysis.
Hello everyone, my name is Jia Liu. I am a senior scientist at EAG. My talk today will be covering the surface analysis techniques for contamination. Here are the three different techniques that my talk will be covering today, which is XPS, OJ analysis, and top SIMS analysis. While XPS and OJ are both good for providing full elemental analysis except for hydrogen and helium, XPS can also provide chemical state information, while OJ is good for small spot analysis with mapping capability. In comparison, top SIMS is very good for organic analysis, providing organic fragment information with excellent detection limits. It's worth mentioning that all three of these techniques are very surface sensitive, ranging from the top 1 to 3 nanometer of the sample surface to 5 to 10 nanometers of the sample surface. So the general question that we usually get at the beginning is, what is this contamination? If you don't have any idea of what the source of the contamination would be, XPS will be a very good starting point because it measures all the elements except for hydrogen and helium with the detection limit down to 0.1 atomic percent. Here is a X-ray induced secondary electron image. By obtaining this SXI image, we can see where the residue is located and selectively put an analysis point on and off the residue. By analyzing these two areas, we will then get a survey spectrum on each area showing what element is present on the sample surface. And by obtaining the spectrum of different elements detected, we can then carry out something called a high-resolution elemental scan in looking at the bonding chemistry of different elements. If you have a general idea of what your contamination would be, such as it's a organic contamination, then TOF-SIMS will be a good candidate for analyzing the contamination. Here we have the surface of a flat panel where the blue square indicates the area of interest. And then TOF-SIMS will provide a total ion image, while the brighter color of the image showing higher ion counts of the area, while in addition to that, we also get a total area mass spectrum showing all the elemental and molecular species detected within that area. By selectively looking at signature species, we can also see how different species were distributing within that area. So we can see here on the bottom right, on the residue surface, we have higher intensity of a PDMS fragment signal, indicating that the residue is likely silicone. If your contamination of interest is too small for XPS, OJ analysis could be a good candidate in looking at small spot analysis. OJ is very similar to SEM-EDS, but it's a lot more surface sensitive. As we can see here in the schematic, the little yellow section is how deep the OJ information depth is, which is very surface sensitive, whereas you have the darker purple section that indicates the SEM-EDS information depth. Here is an image of how a OJ image looks like, that while the blue and red dot indicates the two analysis points that we can put on the residue, and the third point is a control area. It's worth mentioning that the scale bar of this image is 1 micron. OJ spectrum then shows high sodium level on the defect area, while only very low amount of sodium was detected on the control area. We then carry out a sodium map, confirming that the sodium was mainly distributed on the residue surface. What if you need to look a little deeper? What if the contamination is deeper than a few nanometers? Then depth profile analysis can be carried out. If your material is inorganic, monoatomic ion beams would be suggested because they're good. They can remove inorganic material effectively. These can be done by both XPS and OJ analysis. If you have an organic contamination, gas cluster ion beams would be suggested because they're much more gentle than the monoatomic argon ion beam, and they're very good at preserving the organic molecular information. These can be done by both TOF-SIMS and XPS depth profiling. So, some of you might ask, what if my sample is air sensitive? We do have air list entry for air sensitive samples, so please feel free to reach out for us to see what is the best option for you. If you don't want to sputter your sample, but the contamination is a lot deeper. Then we do have our other presenters later on that will cover both techniques for contamination, as well as, so all three techniques that I just mentioned, they were surf-sensitive techniques, and they were performed under high vacuum. If your sample is not vacuum compatible, then there will also be techniques that does not need ultra high vacuum that will be covered later on of the talk. And now let's move our talk to the organic contamination by Dr. Yannicka Schneider.
Thanks so much, Ja. I will be talking about organic contamination. And here is the SMART chart with the 3 organic techniques I'll focus on today. Now, there are actually a number of ways to measure and detect organic contamination. We have spectroscopic techniques such as FTIR, Raman, nano-IR, and they are shown here in these red bubbles. We also have chromatographic techniques, which are GCMS and LCMS. And you can see them here kind of on the outside. The chromatographic techniques are bulk, while the spectrographic techniques, except for NMR, have different sensitivity, with Raman and FTIR having a similar kind of depth of penetration, and nano-IR being much more surface sensitive. So the type of analysis, whether you're going to be using the Raman or FTIR or nano-IR or any of the other techniques, depends on the type of contamination. So first of all, is this a visible contamination or is it invisible? If it's not visible, it's probably better to start with the surface sensitive techniques discussed earlier. Another question is it an organic or inorganic? Sometimes that's not really obvious. And so it's probably a good idea to try both an organic technique and also a different technique like elemental to help with this characterization. Now, is it on the surface or is it kind of a bulk? Is it a defect like a particle shown on the side here? So that really is going to tailor what technique you're using. And also, is this a trace level contamination present in a low concentration, or is it one of the main impurities that you're looking for? And finally, what's the size of the sample? And is the contamination volatile? Is it going to evaporate quickly? So I'll start with a quick FTIR example. So this is a haze that was found on a lens, and it is determined to be a phthalate ester using FTIR, and you can see that the phthalate reference matches the haze very well. So another example is Raman. So Raman is really better. Raman and FTIR are very similar, but Raman's better for very small samples that are maybe 1 micron in size. So here we have a SEM image of a particle. It's a little over a micron, and using Raman, we can clearly identify it as polyethylene. This would be too small for FTIR. Now, to compare the 3 techniques, FTIR, Raman, and nano-IR, we can see that we have different spectral range. Probing depth is also can be varied with FTIR. With Raman, it's about a micron, and nano-IR can be very small. And really, the big thing that differentiates these techniques is the spot size. So nano-IR, you can get down to 30 nanometers, while Raman is, really ideal between 1 and 10 microns, and FTIR is 20 to 100 microns or larger samples. So another comparison of these techniques is shown here on the table, and then we're also adding GCMS to the mix. And so here's an example. We have an organic molecule, ethyl acrylate. We have an FTIR spectrum and a Raman spectrum of this sample. So in the FTIR, we have a really strong carbonyl peak, and that's shown here. But in Raman, the carbonyl is much weaker. In addition, we see that the double bond is shown by FTIR between 1639 and 1622 is a fairly weak peak, but in Raman, it appears as a very strong peak at 1637. So you can see how the carbonyl versus the alkene functionality has different intensities in the FTIR versus Raman spectra. And so that's shown here in this table. In FTIR, the carbonyls are very strong, but in Raman they are weak. Conversely, double and triple bonds are weak in FTIR and strong in Raman. There's other molecules that follow this rule, like diatomic molecules such as iodine are strong Raman absorbers, but you really can't see them by FTIR at all. Likewise, benzene rings are rather moderate by FTIR, but really strong in Raman. Now, Raman is actually also very good for detecting elemental species such as carbon. Again, these would not be detectable by FTIR. Now, when you bring GCMS into the picture, you can see that GCMS can detect carbonyls, triple and double bonds, some diatomics, and benzene rings very well. But one thing it can't do is detect anything other than small molecules. That's because GCMS is really a semi-volatile and volatile technique, and only molecules that are smaller than 800 grams per mole can be detected. So anything that can fly will be detected by GC, but it will not be detected. But anything that is bigger will not be detected. So no polymers, no metals, no inorganics or elemental species. One final note comparing these three techniques is the detection limit of FTIR and Raman is 5 to 28%, so they're not particularly sensitive. In contrast, GCMS is very sensitive and can get down to 100 parts per billion. A quick word about inorganics. So you can see some inorganics with vibrational spectroscopy, but the information is limited. For instance, we could see a silicate and a sulfate here by FTIR, and you can see the peak is pretty much appearing at the same wavelength, so you really can't tell which one you have. You would need to couple it with an elemental technique like EDS, XRF, XPS to be able to ascertain is it a silicate or a sulfate. One example where Raman really shines with respect to inorganic molecules is with rust. So Raman has various forms of rust that can be detected, different kinds of iron oxides, and they have really specific spectra. So it makes it very easy to identify rust as, for example, from something like degraded material or dye. Raman also can detect carbonates, nitrates, sulfates, metal oxides, ceramics, and very good for crystalline materials. So while these are not really primarily used for inorganics, they can be used, again, by coupling with other techniques. And one last word about organic contamination, which is liquids and volatile. So if the contamination appears to be volatile, the best technique for it is not going to be FTIR, Raman, or nano-IR, it's going to be GCMS. And with GCMS, you actually have two different ways to introduce the sample. You can inject it directly with direct injection GCMS. Typically, you'd extract with a solvent and direct into the instrument. But this requires you to figure out the right solvent to use, because if the solvent does not solubilize the impurity or contamination, then it's not really going to do much. So another way that you can do GCMS is you can actually take a piece of plastic or metal or whatever material might be contaminated. You can take that and outgas it. And we have this dynamic headspace, static headspace, different kinds of GC techniques that allow us to just flow gas over the sample and collect all the volatiles. And this is a really good, clean way to determine what volatile molecules, contaminants are present without having to figure out the solvent. Now, some questions have come up regarding this analysis. For example, well, how can I tell if the contamination is below the surface? And one way is really to take some good optical images and maybe probe the surface to see where the contamination is. Also, you can take a spectrum of the contaminant and an area away from the contaminant, and that might also help tell that. Which technique provides the most quantitative information? For that, I would say GC is definitely the most quantitative, although Raman, FTIR, NanoIR, they all can be made quantitative by using standards. Yes, both FTIR and Raman can be used to map surfaces, but Raman, we have a lot of experience with mapping with Raman. How do we deal with heterogeneous samples? Well, if there are multiple visible different looking areas on a sample, we would typically examine them separately. So remove different phases and analyze them separately. And so that's the best way. And what is the best technique for liquid contamination? So again, GC is really good for liquid, but sometimes liquids are not volatile. Like Formalin is a really good example. It's a perfluoroether, and it looks just like a liquid. And you try to run GCMS on it, it's not a liquid. You see nothing because it's actually a polymer. So a combination of FTIR and GC would be a really good option for a liquid, provided it's not too volatile. I think that's all for the questions. And now I'd like to introduce my colleague, Luc Picard, who's a senior scientist, and he'll focus more on the metallic and inorganic contamination.
All right, thank you, Yannicka. So for my slides, we're going to go over metallic and inorganic contamination. So first thing we want to do is figure out which techniques are going to be suitable for identifying inorganic contaminants. And we're going to do that by asking a few questions. One, does it provide elemental composition for most elements in the periodic table? Secondly, is it not to be limited to near surface sensitivity? So are we going to be able to do those bulk measurements of particulate matter or possibly a residue film? And thirdly, does it have the ability to provide quantitative analysis, further allowing for specific materials to be identified? An example of this would be a metal flake. Can we really determine what the alloy of that metal flake is? So answers to these questions are going to be able to pinpoint sources, which, as we know, is often the first step in eliminating the problem. When we take a look at our SMART chart, we have a couple techniques that are going to answer some of these questions. Those techniques include SEM EDS, XRF, and TXRF. And as you see in our SMART chart, these are located in the upper right-hand corner, and these are going to allow us to measure varying analytical spot sizes and also get varying limits of detection. Specifically with SEM EDS, we like to look at this as a good first look technique. And with this, we're able to obtain elemental information specifically and most often for small particulate residues. Now, when we move on to XRF, this will allow us to provide quantitative elemental analysis for both matrix and trace elements. And then specifically when talking about TXRF, we can detect and quantify trace element contamination on semiconductor wafers and other smooth, flat surfaces. Here's an example of some data that came from an SEM EDS. Literally, we see we get this good first look technique, and not only are we able to produce high resolution images, we can do a map distribution of elements with micron resolution on those images. Now, when it comes to the quantification of this, it can sometimes have limited accuracy. With XRF, or X-ray fluorescence, we're able to do full elemental analysis of practically any material. So this would include powders, solid samples, and also include wet samples such as pastes. With XRF, we can get accurate quantitative analysis to help better identify the exact composition of an unknown material. And we can actually do this without standards being required. But if we do have access to standards, it will improve the accuracy some. On the right, we have an example of some analysis from XRF featuring two different in-house standards that we had. On the right-hand columns of each of these tables, we'll see the standard composition, and on the left-hand side is the XRF generated composition. As you can see, these match up very closely, and let's note that this is for both majors and minor elements. When it comes to TXRF, or total reflection X-ray fluorescence, this is specifically going to be used to get excellent sensitivity for measuring trace element contamination on smooth surfaces, such as a semiconductor wafer. And the semiconductor wafer is the most common application. Not only are we able to get, those quantitative numbers for you, but we also have the ability to map those contaminants on full wafers, as seen here in the lower right-hand corner. Wafer size for TXRF is going to be from 50 millimeters to 300 millimeters in diameter. And an example of data that we can collect to create a map on a 300 millimeter wafer would be up to 121 individualized points of analysis. We had a few questions that were submitted that I'd like to go over now. One of those would be, what is the accuracy of measurements if you don't know the base material? And to kind of go along with that, this other question, how do you obtain accurate results using WD-XRF without matrix matched calibration standards? So with XRF, we have two ways to quantify results. One would be using our fundamental parameters-based software package, which uses algorithms based on pure element standards and also X-ray physics to give you what we like to call semi-quantitative quantification. And the second would be to actually use reference standards to create calibration curves. Some accuracy differences that we can see between these two techniques, specifically for fundamental parameters, would be less than 1% to 20%. Now, if we had access to those standards, those accuracies can be as low as 0.1% or better. Another question we had asked us what is the difference between XRF and TXRF? The main difference is, the main physical difference is going to be the orientation of the X-ray tube to the sample. With TXRF, the X-ray tube is going to be in such a position where the X-ray beam is literally just glancing off the surface of the sample. And this glancing effect is what allows us to get down to those trace levels. With traditional XRF, it's just more in that V shape, which allows us to get those bulk measurements. What are some matrix limitations for TXRF? We can do all different types of substrates as far as the semiconductors are concerned. We can do gallium arsenide, sapphire, germanium, silicon carbide, indium phosphate, gallium nitride, all different types. The only thing is with all these different substrates, there will be spectral interference that come into play, but this is usually just for a couple of elements at a time, and the only thing it really does is going to raise that limit of detection slightly. And this last question is really kind of summed up in our next slide. Here's a nice table visually showing the types of different contaminations that could be measured or looked at and what techniques are going to match up or give you the best analysis for that type. And you guys can take a look at this to reference it again at any time. So with that, I just want to thank you guys for joining us today. Quickly, why choose EAG? Well, first off, client confidentiality is core to our business. We know without this, there'd be no reason to send us any of your samples. So that's going to be number one on our list. We are established thought leaders in investigative science, and we have an extensive knowledge base and skilled expertise. With that, we have the ability to scale to your demand and meet your time constraints, as we have more than 2,500 instruments worldwide. which offers a multidisciplinary approach to support you. In short, we know how to solve your materials and engineering related product problems. Thank you so much.